This is a video lesson for, what is it going to be, Wednesday? We're going to do Newton's third law. Unfortunately, I can't be here today for teaching the lesson. I'm at a student council thing. So what we're going to try to do today is I'm going to pre-record a video lesson beforehand, and what I'm going to have you guys do is watch this lesson during class. It won't be quite the same as a normal lesson, obviously, because you won't be able to stop me and ask questions. But it will be probably a reasonable substitute for a lesson. My hope is that what you can do is if you have questions, you can pause the video, rewind it, relook over what's there, and then tomorrow when I'm back in class, we can talk about what we covered, see if there's any questions there. So here goes. Hopefully this works well. Make sure to give me some feedback. Let me know if this works in the future for any day I'm missing. So today's topic is Newton's third law. We've already covered two of Newton's laws already. Just a quick review about those first two laws. The first law is basically known as the inertia law. The idea being that an object that once it's in motion will stay in motion unless an external force acts on it. Or perhaps the same thing, an object that is not in motion won't become in motion unless you give it some sort of force to get it going. So we spent a lot of time on one set of notes, basically looking at a lot of pictures of examples. Today's going to be a very similar lesson. I've got a lot of pictures to illustrate Newton's third law. Newton's second law is the mathematical portion of it, and it basically looks like this. I'll write it out here. Newton's second law is that the sum of all your forces, or the net of all your forces, is equal to the mass of the system times the acceleration given. And we just did a lab yesterday where we were trying to find the net force of a car going down a ramp. And so we can do that for almost any system, really. Just need to add up all of the different forces in all the directions, find the mass, and if you were to divide by that mass, you could find the acceleration. And likewise, if we had the acceleration, we could find force, and so on. So, third topic, Newton's third law. This one is also going to involve the F net equals ma formula. You've probably heard this law before. It usually gets phrased like this: for every action, there's an equal and opposite reaction. Normally, people leave off the last word, though, which is force. Often Newton's third law is used like out of context and in other sorts of scenarios in life. I've got some pictures to show you later. But here's the basic concept. Imagine that a guy is about to step out of a boat, basically, right? And if he steps this way out of the boat, I mean, that's going to be with some sort of force. So I could say there's a force, I don't know, maybe a force applied going this direction here, going towards whatever way we're going to call that. We're going to call that, what do we call this, north, going up this way. So that'd have to be west. Okay. Well, in the opposite direction, in the eastern direction, there's going to be a reaction force. And you would notice that because, hopefully this just makes intuitive sense, that the boat will then actually go back the other way. And so that's Newton's third law. When something goes one direction, it often means there's a reaction force in the other direction. So I'm going to start off by showing a lot of photos of how this might work. So here's the first one. It's a picture of a rocket ship lifting off, right? And so, I mean, one of the forces is going to cause the rocket ship to head in this direction here, right? So the rocket ship is actually accelerating upwards. But why is the rocket ship accelerating upwards? Well, because it's pushing exhaust in a downward direction. Similar to the boat. In the boat example, the man steps towards the west and the boat pushes towards the east. Well, here the boat is going to, not the boat, the rocket ship is going to go in an upwards direction because a force going the opposite direction is going to be like its counterbalance. So, here's another example of one. This is if you can't see the photo very well, it's an example of a propeller for a boat. And so, again, a boat propeller is going to push the water backwards, and as it pushes water backwards, it's going to cause the boat to become propelled forward. So often forces come in pairs, in equal and opposite reaction type pairs. Another example here, sports examples are great for this. How does this illustrate Newton's third law? What I was going for on this picture here is that in order for, this is Alexander Ovechkin, to get a slap shot to go, I mean, often you're going to have a force that's moving the puck this way right here. But there is another force kind of in play here. There are forces like, for example, from his skates. And his skates are actually pushing backwards on the ice in order to give him like the stability he needs, like a cut into the ice, pushing back on him so that he can then propel the puck forward. Even if you can imagine that he has his stick along the ice, I know it's no longer there, but there would be some forces in play where like his stick would flex. I don't know if you've ever seen a picture of a hockey stick flexing during a slap shot, but there would be a force in which the ice is pushing back on the hockey stick, and he is pushing the hockey stick on the ice, causing the stick to have the flex that it often will have, and then that flexing motion will cause the puck to eventually propel forward. And so, again, the point I want to make here is that there are often more than one force in play. There's often forces going the opposite direction of what you would think, like, since the puck is going this way, there are actually forces going back the other way as well. Here's a really typical example. This is a book sitting on a table, and we've talked about this before. There is a force pulling the book down. That's the force of gravity. But there is, according to Newton's third law, an equal and opposite reactive force that is keeping the book up. And hopefully you guys still know this. It's called the normal force. So gravity pulls something down, but the normal force is the equal and opposite reactive force, keeping the book up in the air. This last one here, I was meaning more just in humor. Sometimes people will refer to Newton's third law as kind of like a retaliatory sort of idea. The idea here being that like it was like a prank, someone papered their office there, and so they're going to get back at them. Often Newton's third law is, if that makes sense, is described in a way of like getting back at somebody. So you do something to me, and I'm going to do something equal to get back at you. So probably the best way of trying to illustrate this, then, I did a lot of photos beforehand. I pulled these out of your textbook. Hopefully this will make sense here. Imagine you're a volleyball player. The volleyball player is going to hit the ball into the air. I mean, that's the direction the ball is going to go. So the player is going to exert a force on the ball, knocking it this way here. But, I mean, for any of you guys who play volleyball, I mean, you do feel it when a ball hits you. I mean, maybe it doesn't hurt you that bad after a while you get used to it. But, like, the ball is hitting your arms with force. And so even though you're projecting it this way, the ball, I'm just going to circle this here, there is a force exerted by the ball on a player. I mean, this isn't just for volleyball. I mean, if you weren't ready for the ball and it absolutely like smashes you in the face, obviously there's going to be a force exerted by the ball on the player. Typically, I mean, I'm not a volleyball expert here, but you're going to want to hit it in a certain location so that, you can exert the force back properly. Maybe a better example here is as a baseball example. The ball is going to have the bat hit it. So yes, the ball will go this direction here. But there was also a force, the force of the baseball going, it would try to go through the baseball bat. And so the bat does hit the ball, but you could also phrase it as the ball also hit the bat. I want to say that one more time because I think that's kind of important. You could phrase it as the bat hit the ball or the ball hit the bat. And so really both things are happening at the same time. The bat is hitting the ball this way, and the ball is hitting the bat back slightly. I think probably that there still would probably be a net force in one direction over the other. But without that, there is, hopefully that makes sense, the idea that there is forces acting in both directions. Different example here, a skateboarder here. Why does a skateboarder move forward? Well, it's kind of similar to either the rocket ship or the boat propeller. The person here exerts a force on the ground, pushing himself backwards, and the ground then exerts a force back on the student, pushing him forwards. So whenever you're walking, there's actually both forces in play according to Newton's third law. You are pushing on the ground, and the ground is pushing back on you, thereby propelling you forward. Last example here. We're going to cover this a lot more in about a week here. But it wasn't just Newton who discovered this, or it wasn't just Newton discovering this, but eventually they expanded the laws of gravitation to suggest that like say an apple is falling towards Earth, the apple is actually being pulled down towards the Earth because Earth has a gravitational field. We've actually discovered though that technically there's actually a force exerted by the apple on the Earth, where the apple is actually pulling the Earth kind of towards it. We're going to have to hold that thought on this one here. We're not quite to that topic yet. But there is actually a force where the apple gets pulled down, and the Earth is actually getting pulled up. The reason why we don't notice this, though, is the Earth is so massive in comparison to the apple that it's so negligent. I think I'm going to leave that there. I'm going to re-talk about this concept next week when we talk about gravitation a bit more. It'll hopefully make more sense then. I just left this slide blank because I know so often I put extra slides into places and then you don't realize it because it's on the back slide. So what I want to do here is, I think it's 3 different examples. Let me just check here. 1, 2, 3. Yeah, 3 different examples of questions that sort of involve Newton's third law. To be honest, there's not really a lot of specific questions about it. The idea basically is equal and opposite reactive forces. I'd like to focus on one particular kind of question I could ask you though, and it's about tension. Okay, so our goal is going to be to often find tension. Let me give you an example here. You've got a truck tire, and it's placed on a frictionless surface. So we're going to take friction out of this example here. There is a bucket right here that is 5.6 kilograms. And there is a bucket right here that is 8.2 kilograms. And in the middle, there is a tire. And I did give you the mass of the tire. It's 20 kilograms. First question I guess I have for you is, what's going to happen to this system? And hopefully it makes sense to you. Really, there's 2 main forces acting on the system. Well, it's actually the same force. Gravity is going to try to pull this bucket downward. Gravity is also going to try to pull this bucket downward. And hopefully it kind of makes sense here that the 8.2 kilogram bucket is heavier than the other bucket. So the system will actually start going this way here. So first question is really not a new question. We're going to find the acceleration of the system. And one way of thinking of the system is that really you've got just one massive object. Like, rather than having 3 actual objects here, it might make sense just to draw a box and say that there is a force of gravity pulling you this way, and that there is a force of gravity pulling you this way. And the actual system itself is made up of 3 things. There is a 20 kilogram tire, plus a 5.6 kilogram bucket, plus a 8.2 kilogram bucket. And yes, I know there are strings in between them. Typically, we consider those strings to be massless. If I do give you a mass, you can add it in there, obviously. But what we're going to consider is that really all of this stuff right here is the mass of the whole system. So let me just grab my calculator. I've got 20 plus 5.6 plus 8.2. I have a total mass of 33.8 kilograms. So at this point here, essentially, it's irrelevant, the fact that there's actually 3 items here. We're just going to pretend that there's one massive item. I'll draw it like this, maybe a little better. Okay, that works better. All 3 items stuck together, 33.8 kilograms. And we've got 2 forces pulling in 2 different directions. Well, this force of gravity will be mass times gravity. The mass pulling in this direction will be 8.2 kilograms. Gravity, 9.81 meters per second. So I got 80.442. So that's how many newtons should be pulling on the, what do we call that, the right side over there. And then on this side here, the force of gravity is also mg, but the mass of this guy is only 5.6 kilograms times 981 meters per second squared. Hope I don't make any math errors today. For this guy here, I got 54.936 newtons. So the question then asked to find the acceleration. Let me go back up here. Yeah, find the acceleration of the system. So using Newton's second law, the net force is equal to mass times acceleration. The net force in the system then will be 80.442 newtons minus the 54.936 newtons. The mass we're going to use, though, has to be the mass of everything. So that's 33.8 kilograms. And we don't know A, so we're going to solve for A by dividing by 33.8. If I'm going too fast in this section here, maybe just speak up, say something. We can pause the video. We can rewind it a second. Hopefully the idea behind this would be that you can kind of go to some degree at your own pace. When I divided this side over here, I should erase that. I don't really want that on there. When I divide this side over here, I got 0.7546 for the acceleration. Double check that math. I don't see any errors there. Based on sig digs, it looks like I'm only getting 2 sig digs. So we should say 0.75 meters per second squared. And we should really throw a direction on this because it is going one way or the other. So since I didn't actually label this north, south, east, or west, why don't we go with left and right? So this would be accelerating towards the right. So, if you have any questions on that little bit there, maybe just make sure you make a note there. If I by chance make a calculation error that you notice, just make a note of it here, and then I can fix it later. Hopefully I don't somehow screw up on my calculator. If you need to rewatch that step, rewind, rewatch, pause, take a look over it again, make sure that it sunk in. The second part of the question, though, is kind of the new thing. I'm going to ask you to find the tension in both ropes. And so in order to figure out tension, rather than considering this thing to be one big system, it might be better, again, to consider it as like the different sections. So what you could do is you could redraw the box, and I'm only going to draw this section right here. So this would be the pail that's 5.6 kilograms. This 5.6 kilogram pail is really being pulled in two directions. In one direction, it's being pulled by gravity, which we've already calculated. In the other direction, there is the tension on the rope. And the tension is what's actually going to cause it to get pulled in the other direction, if that makes sense. So those are the two forces in play on the 5.6 kilogram bucket. Hopefully that makes sense. So one direction, gravity's pulling it. In the other direction, the tension of the rope is causing it to go in the other direction. And hopefully it makes sense that this tension right here should be greater than this force of gravity, because that's what's going to cause the system to go towards the right. So in order to figure out that tension, then, it might look something like this. The net force in the system. And the system here is really just this one bucket, not the whole thing, but just that one bucket. It's equal to mass times acceleration. Well, this net force here will be equal to the tension force minus gravity. So if I want to find the tension in the system here, to get Ft by itself, I need to add the gravitational force to the other side, and that will get me my tension in that particular rope. Why don't I label these? Why don't I call it Ft1 everywhere? Just because that's a T there. Just because there is more than one tension going on here. So this could be Ft1, and then later we'll solve for Ft2. Hopefully that makes sense. We already know how much gravity is acting on this bucket, though. It is 54,936, because that number is from right here. 54,936 newtons. Then I just need to figure out the mass and the acceleration just of this bucket, though. So now we're back to talking about just this bucket, and so this bucket is 5.6 kilograms. But fortunately, we know how much it's accelerating at because we just calculated that. It's accelerating at 0.75 meters per second. Okay, I need to fix that. There's not enough room in there for all that. Let me try that again. The mass of the bucket, 5.6 kilograms. The acceleration, we just found this, 0.75 meters per second squared. And the force of gravity acting on it would be, where was it? 54,936. Hopefully this makes sense. The tension in the rope then should be based on two things. It should be based on how much mass this bucket has times its acceleration, which is going like up, I guess, towards the right. But we'd also have to add on some extra tension because of the fact that this bucket itself has some gravitational forces acting on it. So I'm going to try to times by 0.75, whatever that number was, without rounding, like 0.7546153, and then add 54.936. So I have a tension in the rope of 59.16 newtons. I think I only get 2 sig digs again, so let's call it 59 newtons. This one's kind of tricky for tension in the rope because it kind of goes in two directions, right? It goes like up for a while, and then it also goes to the right. So I think I could be forgiven if I didn't actually give a direction for this. But I mean, if you really wanted to, you could say it's going up or right. It's kind of doing both. So that's how you calculate tension in a rope. You're going to want to have the acceleration of the entire system. You're going to need that number. But you're also going to want to then consider just that portion of the system. So what I might recommend here is, now that we've calculated the tension in one side of the rope, why don't you guys see that you can try to calculate the tension in the other rope by basically doing the same process. So maybe pause the video, try it by yourself, and then just watch as I do it. So I'm not actually going to pause the video myself here. I'm just going to keep going, but press pause, and then when you're ready, push play again. So to calculate the tension in the other bucket was 8.2 kilograms. It was pulled in one direction by gravity, and in the other direction it was pulled by tension. The difference this time around is when we do our F net equals MA. This one, gravity, should hopefully be greater than the tension. And I was going to call this FT2, I believe, all the way around. Does that make sense? I hope it does. I can't actually ask that question because I'm not there. But the gravity on this case should be more than the tension this way here, because that's what made the bucket accelerate downwards. So, if you'd like, you can actually just plug numbers in here. I'm okay with that. So the force of gravity was 80.442, it looks like. You're going to then have to minus the tension in the one rope to get the mass of the bucket being 8.2 kilograms. And this bucket, like everything else, was going at 0.75 meters per second squared. Hopefully at this point here you guys are capable of doing algebra. So I'm going to skip that step. But essentially, if you bring this guy to the other side, it makes him positive, and all of this number goes the other way. So this number needs to be less than 80.442. So 80.442 minus 8.2 times 0.7546153.846. And I've got a tension in this rope of 74.23 newtons, which would be 74 newtons. There was a third way of solving it. You could have actually found Ft by not considering the bucket over here, but by considering the tire. And so let me try this a third way here. The actual tire itself weighed 20 kilograms, and it is being pulled by Ft2 minus Ft1. So in theory, doing this, I should be able to calculate Ft2 a second way. Ft2 minus Ft1 would equal mass times acceleration. So, how do I want to put this here? Ft2 minus, where is it there? 59.6, it looks like. 59.16. 59.16 newtons. The mass of the tire is 20 kilograms. The acceleration is 0.75 meters per second squared. Add the 59 to the other side, but I'm hoping you guys are good at algebra by now. This should work out the same both ways. I'm hoping so, otherwise I've made a grave calculation error. 20.0 times by 0.754615, etc., plus 59.16. And when I did it this way here, I got 74 newtons again, the same way here. So you could have got 74 newtons using one bucket, or you could have got it using the other bucket. Okay. You might be asking me then, well, how is this Newton's third law? And to some degree, I'd agree, yeah, Newton's third law, it's not exactly what we're looking at here. It's the kind of question, though, where you have a force pulling in this direction here, and you have an opposite force pulling in the other direction here. So I know it's not exactly Newton's third law because it's not exactly the equal and opposite forces, but I thought I'd throw this in this section here because hopefully that makes sense. When you're working on tension in a rope, that tension can be thought of as there's tension, like, let me put this here. I'm going to highlight it a little bit better here. Pen, how can I not get colors going here? There we go. This rope right here, there's tension in like both sides. There's tension this way, coming from the bucket, or you can consider this tension this way, coming from the actual tire. And then same thing for this guy. According to the tire, you could have tension going in this direction right here, or you could have tension going in this direction right here, coming from the bucket. And really, the tension either way should be the same. You just have to keep in mind which direction it's going. So, hopefully that made sense. I'm going to try another example. If you need, though, rewind, watch again. So, new example. Similar concept, but I'm going to throw something new in this time. I'm going to throw in frictional forces, which makes the problem more challenging because last time, really in terms of forces, there was just tension and gravity. Now there's tension, gravity, and friction. So let's see how this changes the question type. First bit, like always, find the acceleration of the system. So probably the best way of doing this is rather than having two boxes that are both 10 and 20 kilograms, let's just say that it's 30 kilograms total. I'm going to tell you that there's a 50 Newton force pulling on this guy here, and there's two different friction forces pulling backwards. One is 6.7 newtons, that's on the 20 kilogram box, and on the other box there's 4.3 newtons pulling backwards. I guess gravity is acting on the system, but gravity is not really relevant to this particular perspective. So really, I guess in this example here, all we have is an applied force pulling forward, and then you've got a frictional force pulling backwards, and a second frictional force pulling backwards. So yes, there is gravity acting on this guy. Yes, there's a normal force acting on this guy, but those two forces really aren't relevant to the coordinate plane we're working in. So Newton's second law, like we're going to use so many times in this unit, the net of all your forces is your total mass times acceleration. And we can probably skip down a step here. You've got 50 newtons pulling one way, but you've got to subtract 4.3 newtons. You've also got to subtract 6.7 newtons. The entire mass was 30 kilograms, so let's solve for acceleration by dividing by 30. 50 minus 4.3 minus 6.7. So I got 39, and then I got to divide by 30. So I've got an acceleration of 1.3 meters per second squared. And that probably fits SIGDIGS perfectly because probably only get 2 anyways. Just so you know, when you're solving a question like this, we always need this acceleration. That's necessary. So now that we know the acceleration, we're going to look for the tension in the system here. And so there's two ways of looking at it. One way of looking at it is there's a 20 kilogram box getting pulled backwards by a frictional force and getting pulled forward by a tension force. Another way of looking at it is there's a 10 kilogram box getting pulled forward by an applied force, getting pulled backwards by that same tension force, and also getting pulled backwards by a frictional force. And so solving this two different ways, we should get the same tension either way. So let's try it both times and hopefully we get the same. Probably the easier of the two ways is to work with the 20 kilogram box. So if I were to draw just a quick free body diagram, there's a 20 kilogram box which has tension pulling it this way, which has friction pulling it back this way. The frictional force, I gotta make sure I get this one right. The frictional force for the 20 kilogram box was 6.7 newtons. So this guy was 6.7 newtons. So we could say is that the tension force minus the frictional force would be equal to our F net. And that would be equal to the mass times the acceleration of just this box. So to find the tension force, it would be equal to your mass, 20 kilograms, times your acceleration, 1.3 meters per second squared. Add on your friction force, 6.7 newtons. And I got a tension in the rope of 32.7 newtons. What this means then, that 32.7 newtons, means that in this direction or in this direction, equal and opposite directions, either way, it's 32.7 newtons. Now, I could calculate that using the first box as well. It should give me the same answer, so let me try it a second way here. So 32.7 is my tension, but let's try it using the other box just to confirm. So for the other box, the first box was the 10 kilogram box, and it has three forces. There was an applied force of 50 newtons. It's getting pulled backwards by some tension in the rope on the other box, and it's also getting pulled backwards by some friction. And so this we're looking for. I expect it though to be 32.7. The friction force on this box is a little lower. They must have different frictions, obviously. 4.3 newtons. So let's solve. The net of all forces would be equal to the applied force minus the tensional force minus the force of friction. That would be equal to mass times acceleration. I'm going to rearrange it right now. I know not everybody's likes to do it with algebra first. They'd rather put numbers in, but I'm going to try it this way. To get Ft by itself, I'm going to have to do the applied force minus the frictional force minus the mass acceleration. So that's by bringing this guy to the other side and bringing mass acceleration this way here. So 50 newtons minus the 4.3 newtons minus his 10 kilograms times his, what was this number here, 1.3? 1.3. Here's hoping it works. 50 minus 4.3 minus 10 times 1.3. I got an answer of 32.7 newtons, which, if I go back up, was the tension in the rope the other way. So I hope maybe this example makes sense as to why I'm throwing this in with Newton's third law. The tension in the rope, if I go back to the example here, like there's a box here, there's a rope, there's a box here. The tension in the rope could be considered tension pulling this way off of one box or pulling this way off of the other box. The tension is the same either way. It doesn't really matter whether you consider it coming from this box or from this box, it is the same. So hopefully that made sense. I've got one more example I'm going to do. This one's probably the most challenging of all three. There's a lot to consider on this one here. So if you have questions on this one here, though, stop and rewind and look over again. Here's our last example. This is probably pretty typical to what I might ask on, like, say, a quiz or on your assignment. Probably quiz. I'll let you know right now. Like, I'm going to give you something like this on your quiz. Basic idea here, you've got your incline, and so we've been working with inclines in the past. The biggest thing to remember on an incline is that there are forces that work like this. There is a downward force pulling you down the hill. There is a normal force this direction here, and then with the way we draw our triangle, probably something like this. Often I say this guy is gravity, this guy is the force perpendicular, and this is that downward force. Hopefully you're pretty good at working with these triangles by now, because we're going to use them quite frequently. Not every question, obviously. One more thought. This angle right here is 25 degrees. Whatever this angle here it is the answer. So the first question here, I haven't even looked at the question yet, but the first thing we're always going to look for is the acceleration as they travel up the hill. So as I read this here, there's actually two items. There's a snowmobile and there's a sled behind him. And so to start with, it may be best to just consider it all as one big item. And as one big item, 1,000 plus 50 means the mass of this whole thing is 1050 kilograms. There's one more force I haven't accounted for here. Actually, two more forces I haven't accounted for here. If he were just doing nothing, the force of gravity that pulls him downhill would pull him backwards. But because he has a motor in his snowmobile, he has an applied force pulling him up the hill. However, there is another force pulling him back down the hill, which is friction. So there's a lot to consider here. It may be best to redraw this diagram then on a flat surface like this. The sum of all of his mass is 1050. There is one force pulling him up the hill, and that would be a applied force. Basically the strength of his snowmobile. But there are two different forces working against him. One force working against him is friction. Friction is going to oppose motion. So if he's trying to go up the hill, friction is going to try to pull him back down. And not only that, but so is the downward force going to try to pull him back down. In theory, yes, there is a force of gravity and there is a normal force. But like Newton's third law has taught us, these two should be equal to each other, and they're also not really relevant in answering this question. So. Okay, other information here. I tell you the applied force is 5,300 newtons, so that's good because I'm going to need some of those numbers. I also tell you that the frictional forces total 500 newtons. I'm going to need to do one more thing. I'm going to have to find that downward force. And so to do that, I'm going to need to find gravity first. So the force of gravity is equal to mass times gravity. The entire mass of this entire system was 1050 kilograms. Gravity is 981 meters per second squared. And so the gravitational force pulling me down was 300.5 newtons. So that was this guy right here. 300.5 newtons. So that's gravity acting, I didn't draw this very nicely, but in theory straight down. Straight down. Didn't draw this very well at all, didn't I? Now, let me erase that stuff inside there. Or just erase the whole triangle, whatever. Straight down, downward force, perpendicular force, 90 degrees. Okay, that's better. Okay, now we want to find this FD right here. So to do so, it's going to be opposite and hypotenuse. So you might have picked up on this. The downward force is always going to be equal to the FG times the sine of our angle. So we need 300.5 times the sine of 25. I've got a downward force of 4353.179 newtons. So hopefully you guys have the same thing. So let me go back to my my diagram here. This guy right here is actually pulling downwards, like gravity itself. The downward portion of gravity is actually pulling back at about 4,053 newtons, which is going to take up most of his applied force. I mean, to be honest, this snowmobile is going to have a hard time accelerating up the hill. It still will, but not all that easily, because it's really trying to overcome both the friction of the snow, which there's a little bit of, and the fact that gravity is pulling it down a bit. So, F net will then be your applied force minus your frictional force minus your downward force. By the way, I mentioned this a long time ago, but you really have to make sure that you label which one is which, because you've got 3 different forces going on here. Just editing this guy right here. I made a mistake, so I've got to refix this. I did a mistake in my math calculations. So the video got edited a little bit in this section here. Hopefully it turns out good. Let me try that again. Your F net would be equal to your force applied minus your force of friction minus your downward force equals mass times acceleration. Okay, so your applied force would be 5,300 newtons minus friction, which was 500 newtons, minus your downward force of 4,353 newtons, equals your mass of 1050 kilograms times acceleration, divide by 1050 kilograms. Make sure you pay attention to all of the digits, because this number here, the 4,353, was actually rounded at some point, so make sure you keep a few more digits there. One more thought. Hopefully you're getting used to dividing by mass. It's almost always the same kind of way you calculate it. Your acceleration is 0.4255. I think I did that right this time. Which with sig digs, I get... Okay, it looks like you only get 2, this 50 kilograms right here, but when we added it to the 1,000 kilograms, we actually used a number of 1050. Which actually still had 4 sig digs. Like when we did 1,000 plus 50, it gave us 1050. So we do have 4 sig digs there. So it looks like my limiting number is 25.0 degrees. So I get 3 sig digs. So I'm going to go with 0.426 meters per second squared. As for a direction, I might just want to say like up the hill. Or I could say 25 degrees. That'll work. Okay, I'm actually going to cut it off here because I want to challenge you guys now to find the tension in the rope. So we've done some examples like this before. I've taken you all the way up to the point of having acceleration. Now I want you to find the tension in the rope. And so I tell you how much friction force there is on the sled. The sled itself is being pulled backwards by 200 newtons. So just to kind of get you started, the actual sled is getting pulled backwards by 200 newtons of friction. It itself is getting pulled backwards by a downward force. So you will have to calculate that downwards force. And it's being pulled upwards by tension in the rope. And you know the mass times the acceleration. And so I want you to solve for this tension in the rope right here. So hopefully that makes sense. I don't want to actually solve that one for you. I'd like to check your work tomorrow to begin class and see whether it made sense. So there's your challenge for the rest of class. This video is running about 45 minutes. So when you're finished that, you can probably take a break for 5 minutes. The rest of class, I'd like you to either work on some of the previous textbook questions I've given you, or work on your lab from yesterday, because that's going to be due next week, Tuesday. So hopefully this all made sense. Like I said, we'll go over this question tomorrow. If you have any questions, write them down. If you need to rewatch the video, it only ran about 40-something minutes, so you should be able to watch it all again if you need to. To summarize the day, basically, Newton's third law basically suggests that for every action, there's a reaction force in the opposite direction. We don't do a ton of questions that are very specific on it, but the main one I want to do involves tension in a rope in between items. And maybe put a star next to this question here. This is a very typical kind of quiz question I might ask you. So for when we write our next quiz, make sure you're ready for this guy. So we'll talk to you